Welcome back. This video will cover how to exploit secondary storage. Our goals are to allow virtual memory to be larger than the physical memory and allow greater multi-programming levels by using less of the primary memory. The solution is straightforward. We store some of the pages from the virtual memory into the secondary storage, such as disk and SSD. When the page to be loaded into the virtual memory is not present in the physical memory, we swap one page in the physical memory with the demanded page on the secondary storage. Because some pages are in the physical memory while others are in the secondary storage, we need a way to differentiate them. We add an extra field in each page table entry called present bit to indicate whether the frame that the page is mapped to is in the primary memory or not. If the present bit is 1, then the page is in the physical memory. Otherwise, it is not in the physical memory. We call the set of pages that are in the physical memory as the resident set of the process. Meaning that they reside in the physical memory. A process's resident set will change over time as pages are swapped in and out of physical memory. So what should the kernel do when a process tries to access a non-resident page? When a process tries to access a page that is not in memory, the problem is detected because the page's present bit is 0. This event, the attempt to access a non-resident page, is called a page fault. If the TLB is managed by the hardware, it is the MMU's responsibility to check the page table entry's present bit and generates a page fault exception for the kernel to handle. If the TLB is managed by the software, since the page is not in memory, there will be a TLB miss. When the kernel tries to handle the TLB miss, it will find out that the page table entry's present bit is 0. Therefore, it will generate a page fault exception. Let's now look at the kernel's page fault exception handler. First, it needs to swap the page into the memory from secondary storage, evicting one page from memory if necessary. Then, since the page is now in the virtual memory, the kernel should update the present bit of the page table entry to 1. After returning from the exception, the application can retry the instruction that caused the page fault. Since the secondary storage is very slow, we'll talk about the performance of using secondary storage. Secondary storage access times are much higher than memory access times. Suppose that secondary storage access is 1,000 times slower than memory access, and the time of memory access is 1 unit. Suppose that there is 1 page fault after every n memory accesses. The time of n memory accesses is n. The time of a page fault is 1,000, so the total time is 1,000 plus n, and the time without using secondary storage is n. So the ratio between using swapping and without swapping is 1,000 plus n over n. If n is 10, then the ratio is 1010, which is about 100 times slower. If n is 1,000, then the ratio is 2,000 over 1,000, which is 2 times slower. As you can see from this calculation, to provide good performance for virtual memory accesses, the kernel should try to ensure that page faults are rare. Some techniques can be used by the kernel to improve performance. Limit the number of processes such that there is enough physical memory for each process. Try to be smart about which pages are kept in physical memory and which are evicted. Hide latencies, for example, by prefetching pages before a process needs them. Next, let's explore swapping strategy. The simplest page replacement policy is the Fifo policy. Replace the page that has been in memory the longest. We see page A, place it on frame 1. Page fault? Yes. We see B, place it here, and page fault. And C, also page fault. Now we have D, and we look back and found that A has been in memory the longest, so we replace A with D. Page fault? Yes. Now we have A, and we look back, and B is the longest, so we replace B with A. Now we have page B, and we look back, and C is the longest. Now we have page E, and look back, and D is the longest. Now we have A, and A is already in memory, so we have no page fault. B is also in memory, so no page fault. Now we have C, and C is not in memory, and we look back and we found that A is the longest. Page fault? Yes. Now we have D, and D is not in memory, and we look back, and B is the longest. And there's page fault. And now we have E, and E is in memory, so no page fault. There is also an optimal page replacement policy for demand paging called min. Replace the page that will not be referenced for the longest time. Min requires knowledge for the future. We have A here, and B, and C. Now we have D, and we look forward and found that C will not be used for the longest time, so we replace C with D. Now we have A, and A is already in memory, so no page fault. We have B, and B is in memory, no page fault. Now we have E, and we look further and we found that D will not be used for the longest, so we replace D with E. Now we have A, and A is already in memory, so no page fault. B is also in memory, so no page fault. Now we have C, and we look further, and we found that A will not be used for the longest, so we replace A with C. Now we have D, and we found that B will not be used for the longest. So page fault. And we have E, and E is already in memory. No page fault. We have 1, 2, 3, 4, 5, 6, 7, 8, 9. 9 folds here. And 1, 2, 3, 4, 5, 6, 7. Only 7 folds here. So we get better result using mean. There is also the least recently used policy. Replace the least recently used pages to exploit locality and minimize page folds. There are two types of locality, temporal locality and spatial locality. Temporal locality means that programs are more likely to access pages that they have already accessed recently than pages that they have not accessed recently. Spatial locality means that programs are likely to access parts of memory that are close to parts of memory they have already recently accessed. To exploit locality, the kernel must know which pages a program is using. However, the kernel is unaware which pages a program is using unless there is an exception. The solution to track page access is by adding an extra bit in the page table entry called reference bit. This bit is set by the MMU each time the page is used. In other words, each time the MMU translates a virtual address on that page, the kernel then uses this bit to do least recently page replacement. We have page A here, so add A. Page fold, yes. Add B, and page fold. Add C, and page fold. Now we have D, and A is least recently used, so we replace A with D. Now we have A, and we look back, and we find that B is least recently used, so we replace B with A. Page fold. And now we have B, and we look back, and we find that C is least recently used. Now we have E, and we look back, and D is least recently used. We already have A in the memory, so no page fold. B is in memory, so no page fold. We have C here, and we look back, and E is least recently used, so we replace E with C. And there's page fold. And we have D, and D is not in memory, and we look back and find that A is least recently used, so we replace A with D. And there's page fold. And now we have E, and we look back and find that B is least recently used, so we replace B with E. And there's page fold. The clock algorithm, also known as second chance, is one of the simplest algorithms that exploits the use bit. Clock is identical to Fifo, except that a page is skipped if its reference bit is set. The clock algorithm can be visualized as a victim pointer that cycles through the page frames. The pointer moves whenever a replacement is necessary. We have 1 and fold, and the reference bit is set. And 2, there's page fold, and the use bit set. 1 is already in memory, so no page fold. 3 is not in memory, so we place it and set its reference bit. 2 is already in memory, so no page fold. 1 is already in memory, so no page fold. Now we have 4, and 4 is not in memory. All use bits are set, so we use Fifo Policy and look back. 1 has been the longest, so we replace 1 with 4. And clear the use bits of 2 and 3. And there's page fault. Because 3 is used, so we set the use bit of 3. No page fault here. Now we have 1, and 2's use bit is not set, so we replace 2 with 1. And set 1's use bit. Now we have 1, and 1 is already in memory. So no page fault. Now we have 2, and all use bits are set, so we look back and find that 3 has been the longest, so we replace 3 with 2. And clear the use bits of 4 and 1. Now we have 4, so we set the use bit of 4 as 1 again. No page fault here. Now we have 1, and 1 is already in memory, so we need to update its use bit. No page fault here too. Now we have 5, and we look back, and 4 has been the longest, so we replace 4 with 5. And clear the use bit of 1 and 2. There's page fault. Now we have 6, and the use bits of 1 and 2 are not set. So we replace 1 with 6. Now we have 2, and 2 is already in memory, so we update its use bit. There's no page fault here. And we have 1, and all the use bits are set, so we use Fifo Policy. And look back, and we find that 2 is the longest, so we replace 2 with 1. And clear the use bit of other 2 pages.
By the end of this video, you are expected to know why we want to exploit secondary storage, what changes need to be made to the MMU to use secondary storage, page fault, techniques to improve performance of swapping, page replacement policies, FIFO, mean, LRU, and the clock.